Why study the universe? What's the use of studying the universe? It's merely satisfying human curiosity. Well, that's not entirely wrong, considering that the root of science is indeed the fulfillment of human curiosity. So, today, let's indulge in some creative thinking from the perspective of curiosity. Suppose, using existing scientific theories and disregarding technological feasibility, we attempt to construct a universe. The current description of the universe is primarily based on the theory of general relativity. Can we build a universe using the principles of general relativity? We know that general relativity states, matter tells spacetime how to curve, and spacetime tells matter how to move. In essence, it's a theory designed to describe gravity, focusing on the macroscopic structures of the universe. However, to build a universe, we must consider not only the macroscopic structures but also the microscopic particles that make up everything. Building everything starts with building particles, and building particles naturally involves quantum mechanics. In today's particle physics based on quantum mechanics, the Standard Model is the most reliable theory. It not only describes various fermions that constitute matter but also encompasses various bosons that mediate their interactions. Could we construct the entire universe by applying the Standard Model of particle physics to generate all the basic particles? Unfortunately, that's not the case. First, the Standard Model is not perfect. There are still many unresolved questions. For instance, why do neutrinos have mass? Why are there no right-handed neutrinos? What's the origin of the Higgs boson's mass? Moreover, the Standard Model lacks certain particles, like the graviton and unknown dark matter particles, which remain unresolved within this framework. All these indicate that the Standard Model is not the ultimate theory. To construct a universe of everything, we naturally need a theory that explains it all, a theory of everything. One candidate for such a theory is string theory. Discovered in advance by humans, string theory includes not only all the elementary particles in the Standard Model but also the graviton, which describes gravity. Furthermore, by introducing one-dimensional strings, this theory avoids the divergences associated with point particles in the Standard Model. With the foundational theory selected, we can now move on to practical implementation. Since we're constructing a universe, not creating one, we don't need a Big Bang. We just need an original energy. However, this energy isn't conventional energy but rather something resembling initial conditions, a kind of first driving force of the universe. Under the influence of this first driving force, we use strings in various vibration modes to construct all sorts of elementary particles, including those in the Standard Model and beyond. At this point, the source of particle mass is no longer the Higgs mechanism. Instead, it's unified through string vibrations. This process is somewhat like playing a violin, where an A major scale might excite an up quark, and a C minor scale might excite an electron, and so on. In string theory, strings can be open or closed. Open strings are like pieces of string, while closed strings resemble elastic bands used in hair ties, except they are one-dimensional structures without thickness. The elementary particles excited earlier belong to open strings, while building gravity requires the excitation of closed strings. Since constructing basic particles using strings is feasible, building the entire universe from these basic particles is just a step away. The question now is, how do we construct these strings? In the M theory of string theory, the solutions of supergravity equations are not one-dimensional strings but two-dimensional membranes. In other words, a three-dimensional membrane, when curled up in one spatial dimension, becomes what was previously thought of as a one-dimensional string. This one-dimensional string extends between two higher-dimensional membranes, and the mass of particles excited by it is proportional to the distance between these two membranes. We can generate different elementary particles by controlling the distances between different membranes. When we need massless particles like photons and gluons, we simply bring the two membranes together. Whether massive or massless particles, fermions or bosons, they can all be constructed using the method of controlling membrane separation with strings. With this method, constructing matter and energy presents no issues. However, A bug emerges at this point. The photons we construct have non-zero mass. To address this bug, we need to introduce additional spatial dimensions. In the M-theory, our space needs to be 10-dimensional. Beyond the 3 dimensions we can perceive, there are 6 finite-sized dimensions. The space formed by these 6 finite dimensions is the Calabi-Yau space. Calabi-Yau space, also known as a Calabi-Yau manifold, is a compact and matter-free supersymmetric space. In simpler terms, it's a finite space that even without matter has a gravitational field. According to the general theory of relativity, the presence of a gravitational field implies the presence of matter since matter tells spacetime how to curve. However, in Calabi-Yau space, the space itself is already curved, and the need for massive objects is unnecessary. It inherently possesses a gravitational field. It seems that string theory can only be internally consistent in a higher dimensional universe. Thus, we need to construct a higher dimensional space like Calabi-Yau. Only through this higher dimensional space can we generate particles that conform to the properties of familiar particles. However, we can only perceive 3 spatial dimensions, so what does a higher dimensional space look like? This higher dimensional space is not like the interdimensional access depicted in the 3-body problem, nor is it time travel. It's important to clarify that we're discussing spatial dimensions, not time dimensions. You can think of Calabi-Yau space as a separate small space, on the scale of the Planck length, completely unrelated to our macroscopic 3-dimensional space. The real Calabi-Yau space is likely a twisted form. Theoretically, there could be various twisted forms, but for the purpose of constructing a universe, we don't need to consider too many. So, by utilizing high-dimensional Calabi-Yau manifolds and 2-dimensional membranes, we can create various elementary particles, then continue to create composite particles like baryons, followed by atoms, molecules, and complex matter. At this point, a universe quite similar to ours has been created. Oh, it seems we've forgotten something: dark energy. However, that's not a major issue. After all, we're not starting from a Big Bang, so we don't need to wait for it to evolve gradually. We can directly construct a mature, finished product universe that won't undergo accelerated expansion. Although the universe we've built is strikingly similar to ours, if we truly possessed the capability to create a universe, I'm sure you would want to experiment with building one that's a bit different. After all, the greater the power, the greater the curiosity. Now that we're capable of manipulating strings, tinkering with the fundamental parameters of the universe would surely be quite intriguing.